So section 4.2 starts with Rolle's theorem. We're eventually going to build this up to the mean value theorem. And Rolle's theorem assumes three things about a function. First of all, it's continuous on the closed interval of a to b. It's differentiable. And the last part here is an important one, that f of b equals f of a. In other words, at the endpoints, it's at the same y height. So, okay. If that's all true, what this is saying is that there's a point in the middle of a to b such that the derivative is 0. So it has to flatten out. The function has to have a peak or a minimum someplace in the interval a to b if it satisfies Rolle's theorem. So let's apply that to problem number 6 here. And they give us this interval, -2 to 2, and they give us our function f of x. Now we know that polynomials are continuous everywhere, so it'll be continuous on this interval. It's also going to be differentiable there. Polynomials are differentiable everywhere. Now let's take a look at that graphically. So I'm just going to cheat and go over to Desmos. Section 4. Let's see. I sent you out 2 different links for the mean value theorem. This one says more MVT on it. Here's our function, and I just graphed it on the interval from -2 to 2. The nice thing about defining it, instead of doing y equals this, I did g of x. The nice thing about defining it that way is I can do stuff like this. I can say, all right, well, what's g of, say, -2? G of -2, and it gives me an answer, is -6. And I can see that down here. G of -2 is -6. And likewise, g of 2 is also -6. So all three assumptions of of Rolle's theorem are true here. The function is continuous, it's differentiable, and at the endpoints, they're equal. Okay, good. That's what I wanted to see. Now, Rolle's theorem can be thought of in kind of an informal way. The old adage, what goes up must come down, right? And if what goes up must come down, then somewhere in between, it's turning around. It's going to start heading down. And at that point, what happens to the change in the function? The change is 0. It levels off. So you've got a place where the derivative is 0. And that's what we see here. So, problem number 6. Let's just double check here what they're looking for. I think they might be just looking for us to find that point where the function turns around.
So basically what you're saying though is all 3 of those rules have to be correct in order for...
All 3 of these have to be correct in order for Rolle's theorem to apply. So if one of them is broken, then Rolle's theorem may or may not still work. It's not guaranteed. But if all 3 of these things are true, it's guaranteed that there's going to be a point, at least one point in the interval, such that the derivative equals 0. So let's find that point for this particular function. F prime of x is going to be 3x squared minus 4x minus 4. And we want to find where this is equal to 0. Oh, boy. So I'm always torn with these because I'm never really good at factoring these things. Do I want to bother trying to use the quadratic formula, or should I try and factor it? The problem with trying to factor it is if it doesn't factor, then you're stuck, right? Then you got to go back and use the quadratic formula. So your choice. Do you want to try and factor it, or just pull out the quadratic formula right away? Quadratic formula right away? Okay. So let's see. We've got A, B, and C. So it's 3, -4, and -4. So it's the negative of -4 plus or minus the square root of negative 4 squared minus 4 times a, which is 3, times c, which is negative 4, all over 2 times 3. So see if we can't clean that up a little bit. 4 plus or minus the square root of 16 plus 48 over 6. And at this point I got a little egg on my face, because if this number underneath the square root, if the discriminant is a perfect square, then we could have factored it. So it's 4 plus or minus 8 over 6. There's two possibilities. The positive case is 4 plus 8 over 6, which is 12 over 6, or 2. The negative case is 4 minus 8 over 6, which is going to be negative 4 over 6, or negative 2/3. All right, so we're guaranteed to find at least one place where the derivative is 0, and we found two places. Does that contradict Rolle's theorem? No. Rolle's theorem says there's at least one place. If there's more than one place, that's okay. So there's the two places. By the way, in hindsight, this would have factored as x minus 2 times 3x plus 2. Yeah. Okay, how are we looking with that first one, problem number 6? Let's take a quick look back at the function. So there's our point at negative 2/3, but there's also one right there at 2. So you can kind of see that. It's right at the end. Let's keep going. We're going to extend Rolle's theorem to something a little bit more powerful. Rolle's theorem is pretty nice, but we're going to extend Rolle's theorem to something called the mean value theorem. Now, everyone should have a handout, right? Everyone got the handout? So the mean value theorem has a couple of the same assumptions that the Rolle's theorem did. You have a continuous function, and it's differentiable on the interval here, the open interval. So those two assumptions are there, but we're not asking for the function to equal itself at the endpoints. What the mean value theorem is saying is that if you draw the secant line to your function, so there's our secant line. Let me make it a little bit more clear. Let's see. Do we have any rulers here? Oh, here we go. That's all right. Yeah, Sky's got all of them. So there's our secant line. What the mean value theorem says is that somewhere in the interval from a to b, there's a point so that the slope of the tangent line, that is the instantaneous rate of change of the function, matches the average rate of change of the function. That these two lines are parallel. That's what the mean value theorem is saying. And the mean value theorem gives us a lot more than just that. But right now we're going to focus on finding these types of points, and we'll do it with problem number 12. So again, we're going to work with a nice polynomial function. F of x is x cubed minus 3x plus 2. And on the interval 0 to 2. Excuse me, negative 2 to 2. Sorry. Yeah, negative 2 to 2. Now, one of the things we're going to need is the slope of the secant line. So let's do this. Let's make ourselves a little t-table. X and f of x, -2 and 2. Let's put this into our graphing calculator. Let our graphing calculator do some of the work. Feel free to do it by hand, if that's your thing. But x raised to the third minus 3x plus 2. Bam, like that. So there's our function. And hopefully you still have your table set up the right way. So if you want to check it, you can hit second and then the window key. Make sure that the independent variable is set to ask. And with that, we can go to our table, second and table, second and the graph key. Let's delete all the things here with the delete key. And just type in -2 and 2. And we get the y values here, right? 0 and 4. Now, there's nothing wrong, like I said, with getting those y values in other ways. And certainly you can look at this, I hope, and figure out what happens at particular values, but whatever. What we need to find, first of all, is the slope of the secant line. Basically, the slope of the line between those 2 points. So that's going to be m sub secant equals 4 minus 0 over 2 minus -2. So the slope of the secant line is 1. Okay. What the mean value theorem says is that someplace between -2 and 2, the slope of the tangent line has to equal the slope of the secant line. What is it that measures the slope of the tangent line? The derivative. All right. So what's the derivative of f? 3x squared minus 3. Yeah. So 3x squared minus 3, right? So someplace in this interval, in the interval of -2 to 2, the slope of the tangent line has to equal 1. Okay. Well, let's see if we can't. Yeah. But that's looking like a really ugly number. It's going to be. Okay. Yeah, no. I'm just kind of like, wait a minute. This usually works out. We copied down the problem, right? Yep. Let's see. 3. Well, if we solve it, it's going to be 3x squared equals 4. X squared equals 4/3. X equals plus or minus 2 over the square root of 3, which you could rationalize as 2 square roots of 3 over 3. So, okay. So it's at this point that the function should have a derivative of 1. So let's see about that. Let's graph it. So let's adjust our window from -2 to 2. And then we'll let the calculator do the rest. We'll hit zoom 0. So we get something like that. Second calc. Let's find the derivative, dy by dx, at 2 divided by the square root of 3. Wow, how about that? Take a look at our derivative there. It's a decimal value. It's pretty close to 1, but it's not exactly 1. That's okay. That one works. We could also try the other one, but I have a little more confidence now, so I'm not going to bother to go back. But it works. We can see that. And if you actually wanted to, you could probably fit the equation of the tangent line here. But our goal right now is just to find this point. Let's see, decimal value-wise. Yeah, both of these would actually fit in the interval. So if I trace -2 divided by the square root of 3, then yeah, I get another point where the derivative would be 1. Well, I didn't do the derivative thing. If I want to do the derivative thing, let's see, let's go back here. dy by dx, that tells you the slope of the tangent line, and I should be close enough. I should about get it. No, I guess I wasn't. Slope of the tangent line at -2 divided by the square root of 3. Yeah. So the reason you're not getting a perfect slope of 1 is because it has to do it numerically as opposed to what we do is algebraically, but it does verify that. So looking good there. Okay. How are we looking with problem number 12 there? In all of these, you're going to have to find the slope of the secant line, which is really going to come from a table like this, and set it equal to the derivative and solve. And that's going to give you your point guaranteed by the mean value theorem. Yeah. Now sometimes some of these numbers might be outside the interval. And that's okay, it's just that they're not the points that are guaranteed by the mean value theorem. So yeah, that'd be kind of a gray area for me. If you got some answers that weren't in this interval, then they shouldn't be part of your answer for the points guaranteed by the mean value theorem. Yeah, I'm not sure what I do in terms of grading. At most, I would take off a point. But chances are you might just get a frowny face, which is almost as bad as losing a point. But yeah, it could be worse, All right, let's try a different one. Problem number 16. F of x is e to the negative x, and we're going to work on the interval 0 to 2, which I think is what I said for the last one, but this time I really mean it. Now, I don't think I need to bother to plug this into my graphing calculator and get some decimal values. I'm just going to work with it here, particularly because the first one, e of 0, should be pretty easy, right? Make me look good. All right, good. Yeah, you missed your chance. All right. Well, tell you what, how about the next one? What do I get when I put in x equal 2? E to the negative 2. Cool. So, all right, we need to find the slope of this line now. So the slope of the secant line is just the slope of a line, right? It's the difference in the y-coordinates divided by the difference in the x-coordinates. I'm giving you a chance to write this for yourself first, okay? Just to double check that you know it. Your chance is fading. Hurry up. All right, so in the numerator, it'd be e to the negative second minus 1 over 2 minus 0. You want to subtract things in the same order. So this one minus this one divided by this one minus this one. So I get overall e to the negative second minus 1 over 2. Not exactly a really friendly expression. That's okay. All right. let's come down now and work with the slope of the tangent line. Slope of the tangent line is given by the derivative. So, as far as the derivative is concerned, what's the derivative of e to the negative x going to be? Excellent, thank you. So it's e to the negative x, and just the function itself, times the derivative of the exponent. The derivative of the exponent is negative 1. So let me write that as negative e to the negative x. And as ugly as it seems, I've got to set these two things equal to each other. Okay. It's a little bit ugly. Now, I'll tell you what. Before we actually solve here, let's go over to our Desmos link. And this is the one that I want. So it says the mean value theorem is the one that we're looking at. And I've got in black, I've got the graph of e to the negative x. And then I've drawn the secant line here. So I want to manipulate the point where I find the tangent line so that these two things have the same slope. And you can manipulate that with C. You want to find C so that it's pretty close to perfect. And you get pretty close, but it's hard to get exact. So here's the slope of the secant line as a decimal, negative 0.43, etc. And here's the slope of my tangent line, which, all right, not too close. Let's see if I can get a little bit better. But I want to get really close. So I want to solve for this point exactly. Let's see if we can't do that. That would mean solving this equation. So it's negative e to the negative x equals e to the negative 2 over 1, or minus 1 over 2. I think the first thing I'll do is I'll start by getting rid of this negative here. I'll multiply both sides by negative 1. So I get e to the negative x equals, and here's my little trick for getting rid of the negative. I'm just going to change the order of the subtraction here. Instead of e to the negative second minus 1, I'll put 1 minus e to the negative second. So that changes the order, and that gets rid of the negative on the right-hand side. Well, how do I solve from here? What would you do to try and solve for x? No. Take the natural log. No, you don't want to multiply by 2 because that would put the 2 over here and you're trying to get the x by itself. So I'll take the natural log, ln of e to the negative x equals the ln of 1 minus e to the negative 2 over 2. And this is beautiful over here because that becomes negative x. And if I multiply both sides by negative 1, even though it's not really a very friendly looking number, this should be the point at which I can type in and get the slope of the tangent line to equal the slope of the secant line. And numerically speaking, this is about 0.83856. That's about what that is. So at that point, I should see the slope of the tangent line equal the slope of the secant line. I'll let you catch that up, and then we'll go back to our handout or our Desmos link and check that, see if it works. So let's type in the exact value that we need for C, and watch what happens to the slope of the tangent line, that is the derivative here, compared to the slope of the secant line. They should start to get pretty close. So 8, 3, 8, 5, 6, And look at that. We got pretty good agreement in terms of those slopes. So definitely happy on that one. Okay. Comments or thoughts on these? I mean, I hope these aren't hard problems. The one thing you want to keep in mind is you got to find this slope and set it equal to the derivative of this function. If you're not finding a derivative in this class while you're doing a particular problem, at some point you might want to think about it. If it's not going to involve a derivative or a limit, then something might be wrong, because this is a calculus class, and that's the kind of things we're going to do here. No comments or any thoughts on this? Ugly? Yeah, it's kind of an ugly one. I'll even admit that. This is an ugly point. But it worked. One last one from this section. Problem number 18. Okay. So problem number 18, we've got this function f of x is 2 minus the absolute value of 2x minus 1. To show there's no value of c such that basically the mean value theorem is satisfied. And then it says, well, why doesn't this contradict the mean value theorem? What it's saying, in essence, with this, and I think they wrote it this way just because they didn't want to use another line of space, that we can't find a point C that satisfies the mean value theorem. So, well, let's see what the mean value theorem would say about a problem like this. So, let me copy down the problem here for us real quick. F of x is 2 minus 2x minus 1 in absolute value on the interval 0 to 3. So x and f of x, 0 would be 1. If I had a 3 here, that'd be 6 minus 1 is 5. So 3 would be, negative 3? All right. So the slope of the secant line here would be negative 3 minus 1 over 3 minus 0, which would be negative 4 thirds. Now, why aren't we going to be able to find a point to the tangent line, or a tangent line with a slope of negative 4 thirds? Well, it is an absolute value. Let's take a look at the graph, and maybe the graph will help jog your memory a little bit. So I'm going to go over to this one. So this is the more MVT link, and graph these points. So I just graphed this for the interval of 0 to 3, which is where we're interested in. And I think I'm going to have a hard time finding a line with a slope parallel to 4 thirds. But the mean value theorem isn't wrong, though. Because the mean value theorem doesn't guarantee that I'm going to be able to find such a point in this case. Can you understand why? Ooh, somebody got that. Bonus points here. Who got it first? Bonus points. Well done. Remember, one of the things that is required from the mean value theorem is that your function is differentiable. I pressed the wrong one. There we go. It has to be continuous and differentiable. And if you look at our graph here, where is this function not differentiable? Yeah, right here at the corner point. So because it has a corner point, it's not differentiable, and the mean value theorem is not satisfied. The conditions of the mean value theorem is not satisfied, so it won't guarantee that this point exists. And it doesn't. There's nowhere you're going to find a point that's tangent to this with a slope of negative 4/3. Just not going to happen. All right. Well done. Well done. So, any questions or thoughts on problem number 18 here? Okay. Good luck with the homework, and I'll get you those in just a minute.